Let's talk about the first category of intermolecular forces known as dispersion forces. Again, to repeat a definition, these are simply fluctuations in the electron distribution in atoms and molecules resulting in a very temporary dipole. The key here is that they're temporary. In a region that has excess electron density, we're going to see it develop a negative charge. In a region that has a depleted electron density, it will have a positive charge. The attractive forces caused by these temporary dipoles are known as dispersion forces. I always hear them called London dispersion forces. Every molecule, every atom will always have the ability to distribute a dispersion force. A temporary dipole is established in one molecule as it induces a pole in all surrounding molecules. Every atom and every molecule, if it becomes so close to another, it can temporarily create a region of positive and negative. A dispersion force manipulates electron density temporarily. Here's a nuclei of a helium atom. 2 protons, 2 neutrons. Here are its 2 electrons. If at a particular moment in time both electrons are near each other, that creates a distribution that's a little bit negative on one side, a little bit positive on the other. If we see one helium atom with an electron density of a negative cloud coming near a positive cloud, we set up a dispersion force. Notice they're doing a little dashed line. It's a weak attraction that's a temporary attraction just based on manipulating electron density. An instantaneous dipole on any one helium atom may induce an instantaneous dipole on a neighboring atom, and then you see this attraction. It's temporary. It does not stay in this position. Soon as these electrons become so close, electrons repel. This will go back to an equal distribution. Dispersion forces are very temporary. The magnitude of the induced dipole depends upon several factors. Polarizability of the electrons, which is really talking about the volume of the electron cloud. The larger the molar mass, the more electrons that atom has, the bigger the atom are. The larger the electron cloud becomes, the more we can induce a dipole. Increased polarizability just means an induced dipole equals stronger attractions. Bigger atoms, heavier atoms, stronger dipole inducement. The shape of the molecule can also influence a dipole. If I have more surface-to-surface contact, a larger induced dipole equals a stronger attraction. The larger the molecule, the larger the attraction. Long hydrocarbon chains will have a better induced dipole. So in this particular graph, I know there's some overwriting here, but let's make some sense. These are the noble gases, and the molar mass is definitely increasing as the size of the atoms increase. They get heavier as you go down a column. I can clearly see that the boiling point follows that same attraction. The larger the atom, the greater the London dispersion force, again due to the manipulation of the larger electron cloud. The stronger the dispersion force creates a higher boiling point. Molecules have a greater attraction to each other the heavier they are, and therefore will have a higher boiling point. Heavier the molecule, the bigger the molecule, the stronger the dispersion force, the higher the boiling point. Relationship between boiling point and molar mass of nonpolar molecules, such as those noble gases, halogens, or this is just any element, XH4, could be like methane. You can see a clear distinction. Boiling point definitely increases as the molar mass increases. Going from left to right on a period, the atoms are getting heavier. Boiling points will increase. Properties of straight chain alkanes. 1 carbon in methane, 2 carbons in ethane, 3 carbons in propane, 4 carbons in butane, 5 in pentane, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1 carbon being added each time to the hydrocarbon chain. What we notice is a trend. The bigger the molecule, the heavier the molecule, the higher its boiling point. MP stands for melting point, again steadily increases. And its density will increase. The heavier the molecule, the more London dispersion force, the greater the attraction between the molecules. There's more electron density to manipulate to create a dipole moment. Pentane with 5, hexane with 6, heptane with 7, octane with 8, nonane with 9 hydrocarbon chains. Those numbers of carbons. Molar mass will increase. The heavier the molecule becomes, the higher the boiling point. The stronger the intermolecular London dispersion forces. Same trend. As molar mass increases, boiling points increase, melting points increase due to the strong intermolecular attraction. The effect of molecular shape on the dispersion force, and again, think about surface area. The more surface area we have to come into contact between the molecules, the stronger the dispersion force will be. So if I have a long hydrocarbon chain versus one that's kind of more circular, long drawn out, or more around a central atom, notice the trend. The molar mass, they're pretty equivalent, 72.15 for pentane. But in neopentane, 72.15. Let me kind of draw this to make sure we're understanding. This is a long hydrocarbon chain, just 5 carbons in a row, and those are hydrogens coming off like this. So a long carbon chain is a long surface area. However, here in neopentane, they arrange the carbons a little differently. They attach them back to a central atom. 1, 2, 3, 4, 5 carbons. But instead of in a straight chain, they've got them arranged back to the central atom. And yes, there's still hydrogens coming off there. So it's the same number of atoms, just rearranged a little differently. The longer the chain, the more opportunity to create surface area contact, and therefore more London dispersion force, and therefore a higher boiling point. Same molar mass, different arrangement. The one that has more surface area creates more intermolecular attraction and will have a higher boiling point. Clearly, normal pentane, N-pentane, 5 in a row, boils at a higher temperature than neopentane, less surface area to create London dispersion forces. Branch chains have lower boiling points than straight chains. The straight chain isomers have more surface-to-surface contact and therefore create more intermolecular attractions, more opportunity to induce a dipole called a London dispersion force. Choose a substance in each pair with a higher boiling point. We're asking ourselves, thinking about molecular mass and surface area. Here we have a methane molecule, CH4. Here we have a butane molecule, C4H10. Clearly the molecular mass is larger in the second structure. Higher molar mass, larger surface area will create more London dispersion forces and therefore a higher boiling point. Pick the heavier molecule, long straight chain. Now in letter B, C6H12 is